Hello everyone. Today I'm talk about a multi-stage heuristic approach to electric vehicle routing with pickup, delivery and optimized charging using clustering and local search. What is electric vehicle routing problem? EVRP. The EVRP is modern delivery challenge that focus the electric vehicles EVs unlike regular fuel powered delivery trucks. EVs run on batteries which can only fast for limited distance before to needed to recharge. They created a new challenges when planning delivery routes. In regular vehicle routing problem VRP, the main goal to find the shortest path or fastest way to vehicle to deliver goods. But the EVRP we also have think about like battery limits, where uh, where charging station are located, when and where vehicle should stop to recharge. The study in this paper to look at different delivery situation in the city, such as small areas with fewer customer, more vehicles, and larger areas with more customer demand but fewer vehicles. Why EBRP important in cities? In the cities are getting busier and more people shopping online and expecting for fast delivery. At the same time, there is the growing pressure at reduce air pollution, traffic, fuel, electric vehicles, cleaning and quieter than gas powered vehicle, making them a great choice for urban deliveries. However, using EVs also bring problems like limited battery life. Limited battery life have interrupt deliveries if the vehicle runs out of power. And the second, the few charging station. There has the problem for drivers must plan carefully where to recharge. The another problem by solving the EVRP we can solving by help delivery companies save energy and time, make customer happier with faster deliveries, reduce pollution in cities by in traffic, support smarter city planning by showing where charging stations are most needed. Uh, this paper, the EVRP goals of study. The EVRP aims to create the smart deliveries plan to EVs by solving the EVRP. The main objective are the reduce energy. It means the plan efficient route so vehicle can little battery power as possible. Minimize travel distance. Make sure the routes are short while still visiting all customer locations. Ensure vehicles can complete their routes. Respect limit on how much weight they can carry. The main objective of this EVRP, how to minimize the energy consumption and how to reduce the energy consumption and reduce the delivery time.
So as we gone through problem statement, our main goal is to uh, minimize the total energy consumption of a vehicle and also total travel distance. So we made objective function combining the both the parameters. So here this Cij into Ij indicates the travel distance, and this alpha into Dij into Wij indicates the energy consumption, where Cij is nothing but a travel cost from node I to j. Xij is a binary variable, 1 if route is taken and 0 is if no route is not taken. Dij is a distance traveled from node I to j. W is weight carried from node I to j, and alpha is nothing but a energy consumption rate, which is a constant. And uh, we we add this, we summation this, and minimizing this equation will be the objective function. And as we gone through the problem statement, we have some constraints, some rules, some to follow. So uh, uh, here are some constraints or mathematical formulations. Vehicle capacity should be uh, less than uh, W max. So each vehicle is set to some weight capacity which is W max. So vehicle should not uh, exceed that weight limit. And battery level constraint, where each EV vehicle electric vehicle is set to some battery limit. For example, in this problem we set to 15%. So if vehicle battery level is less than 15%, in then it needs to recharge its battery. And a charging station, so each charging station is have some charging rate R. And energy consumption constraint, so energy consumption constraint is given by this alpha into Dij into Wij, where alpha is the energy consumption rate. So after this we move to a algorithm. Our main so this is a pseudocode for our algorithm. The algorithm is hybrid clustering and heuristic search for EVRP. So initially we compute the Euclidean distance matrix for all the node pairs I and j, and we define an energy consumption function which I mentioned previously. And we uh, customer clustering. So here we partition the customer set C into k clusters using a k-means algorithm, where k is nothing but a number of vehicles. So if, for example, if there are 20 customers and 4 vehicles, then we divide that 20 customers into 4 parts, so that each vehicle can travel to that uh, customer cluster clusters. And uh, we used a heuristic method called nearest neighbor heuristic. So here we initially define the route define the route RK, and current location dw, weight as a WK, energy as a EK, distance DK, and energy consumed ECK, and charging station CHK, where this K prefix denotes the vehicle, certain vehicle. And this CK is the customers in a certain cluster. So while so initially we take customers in that cluster. So initially that is unvisited nodes will be null. So we select the nearest unvisited customer from a depot. So every time we move to that cluster customer node, we calculate the weights, projected weight, where projected weight will be q next and qp are the delivery and pickup demands. So in current weight we subtract the q next, which is the demand, and we add the p next, which is the pickup. So calculate and after that we calculate the energy required to move to next customer node. So also we fourth step is to check a weight capacity. If the weight capacity exceed the W max, then we compute the energy required to move to that vehicle move to depot. So if the energy required to vehicle move to depot is less than the minimum energy, then it selects the nearest station to charge the vehicle. So if and next if it calculates the energy required to move that nearest charge station. If that constraint satisfies, then it adds the route S to route set of route RK, and update the distance DK, and energy consumed EK, and energy current energy of that vehicle. So it the energy current vehicle energy will be discharging, so it is given as a negative symbol here. And after that it checks for energy capacity. So if energy capacity less than minimum energy, that is 15%, then it select a nearest station and it computes the energy required to move to that station. And if the energy is greater than that, then it updates the yeah, it appends the s to rk and update the uh, decayed energy consumed. So after that, visited customers. So certainly, like this, it visits all the customers updating rk, dk, and eck, where it denotes the route set and distance and energy consumed. So after visiting all the nodes, it needs to return to the depot, and to report to a depot, it calculates the energy required to return to the depot. And if the energy is less than e minimum, then it selects the nearest station, and then it calculates. If the energy is greater than minimum capacity, then it moves to a uh, then it appends the s to rk, update the uh, distance, update the energy consumption, and record the charging station ch, which charging station it is charged. After that, we uh, to optimize that travel path in the certain cluster, we use a route optimization technique, that is 2opt. So here, for each segment with a multiple customers, apply 2opt. It iteratively swap edge pairs until no further distance reduction occurs. So if the vehicle is traveling from one customers to other, crossing a nearest customer, then it takes a lengthy path. So to that reduce that crossing or swapping the edge pairs, we use a 2opt algorithm. So in final validation, after the vehicle returning to the depot, we reset the all the matrices, that is final decay, final energy consumed, and final energy charge station. So uh, and nextly we return the valid routes are, that is
We will see how the algorithm work using code. First, we need to create a evrp.py file. In evrp.py file, we have to create a class evrp in which you have to call two optimization function value is equal to true. If we don't need this, then we can put the value is equal to false. Similarly, for loading of input, we have to define the function load from file, and for calculating the distance and the energy consumed, we have to also define the function calculate distance and the energy consumed. Similarly, for clustering of the customer, we have to define the function cluster customer. In this, we use k-mean clustering for cluster of the customers. Similarly, for base route, we have to define two optimization function in which it return the base route. Now, I will call this evrp.py file in main.py file. Similarly, for visualization of the route, we have to define the visualization part in visualize.py. In this, we have to define how the routes will shown in the all routes.png along with its weight, pickup and delivery. Now we have to take the input from EVRP file to run the main.py file. For this, we have to create a input.evrp file in which we have to define some parameter, number of vehicles, weight capacity, energy mean, energy rate, charge rate. Similarly, we have to define the node in which we have to define the node for depot, customers and the charging station. For all the nodes, we have to define an ID like 0, 1, 2, 3, 4, 5. Similarly, for 20 customers and for 4 charging stations, there are the ID 201, 202, 203, 204. along with its xy coordinate, means depot x is 29.0 and y is also 29.0. Similarly, customer 1 x is 43.99 and the customer y coordinate is 12.26. Similarly for charging station also. Now we have to define the weight of demands like pickup weight and the delivery weight. So we have to define ID along with its weight. Now you can see that for charging station the pickup and the delivery weight is 0, means they do not need to pick up anything and they do not need to deliver anything at charging station. Now you can see the result in network.png and allroutes.png on running main.py. So for running the main.py, we have to write python main.py. After running python main.py, you can get the different routes for each of the vehicles along with distance covered, energy consumed, charging station and the number of charging event occurs. So you can see here there are 10 vehicles, all have the different path and all have the different energy consumed rate and all have the different distance traveled. Now you can see this in allroutes.png file. You can see here for if we take for vehicles 1, that is orange line denotation. In orange line we have to cover from 0 to 9, means from 0 depot it cover it into 9, node number 9, then it has to cover node 20, then it has to cover node 4, then it has to cover node 16. After serving all the nodes in a cluster, it got discharged. So for charging them, it gets one charging event at nearest charging station, that is 202. After charging at 202, it goes back into depot. Similarly, in different test cases, we can see different map. Like I have done 4 test cases. You can see here. In test case 1, that I will see that I already see this map. Similarly, in test case 2, you can see here you can see different map, route map and the network map. Similarly, you can see different route map and the route map in test case 3 also. Now in test case 4 there are 100 customers, so it also easily cluster all the customers and serve using only 5 vehicles, means how they are efficient, means 100 customers are easily covered by only 5 vehicles by this algorithm. So this algorithm is very efficient. You can see the solve time also in the output. There is solve time of 0.05 second, means it is very less as compared to other algorithm that are already worked in field.
In the conclusion of EVRP problem, it has provided significant insight into optimizing electric vehicles operation in urban environment. The key findings of the EVRP are the effective routing strategies, energy management, and visualization and analysis. Effective routing strategies, we have used k-means clustering, nearest neighbor heuristics, and two-opt optimization, which helped in effective generating insufficient routes for electric vehicles. These strategies minimize travel distance and energy consumption. Energy management. The integration of energy management strategies was crucial in maintaining operational feasibility. It is because we have to monitor energy levels of the each vehicle at each level or each nodes, which ensured that the vehicle did not run out of energy. and it maintain our service continuity. Visualization and analysis. The use of visualization tools like NetworkX and Matplotlib provided clear and intuitive representation of the network and route, which help us in visual analysis and validation of the result, and highlighting of the effectiveness in the routing strategies. Uh, Contribution to the EVRP and related fields. The study contributes to the field of EVRP and related areas in several ways, such as practical applications, algorithmic innovations, sustainability, and policy and infrastructure. In practical application, the finding provide practical insight for logistic and transportation companies looking to optimize their electric vehicle fleet, such as if we order from our online courier partner in the urban city, we can use this method to electrify, or uh, we can show that the real world scenario to improve efficiency and sustainability. Algorithmic innovations. The combination of clustering, heuristic method, and optimization technique offer a versatile approach to solving complex routing problem, and this can be adapted to other domains where efficient routing is crucial. Sustainability. By optimizing routes and energy use, the study supports sustainability goals in urban logistics. Electric vehicles are already more eco-friendly than the fuels ones. The and efficient routing further enhances their environmental benefits and energy consumption and less CO2 emission. Policy and infrastructure. The insights gained can be inform policy and infrastructure development, such as the strategic placement of charging stations and incentive for adapting electric fleets, which can be helpful in urban areas. Limitation and future research direction. While the study provides valuable insight, there are some limitation and areas of future research, such as scalability, dynamic environments, advanced optimization, and integration with other technologies. Scalability. Although the clustering approach allows for scalability, further research is needed to test the solution on larger network with more vehicle and customers. This will help understand the limits of the current approach and identify areas of improvement. Dynamic environments. The current study assumes a static environment with fixed demand and conditions. Future research could explore more dynamic scenarios where demand and condition change in real time, requiring adaptive routing strategies, which can be seen in real time. Advanced optimization. While two-opt optimization was effective, and more advanced optimization techniques such as meta-heuristic or machine learning based approaches could be more explored to further improve route efficiency. Integration with other technologies. Future studies could explore the integration of EVRP solution with other technologies such as smart grid system or autonomous vehicles to enhance overall efficiency and sustainability. In conclusion, the study on electric vehicle routing problem provides the robust framework for optimizing electric vehicle operation with significant implication in urban logistics and transportation. The findings offer practical solution and pave the way for future research in this crucial area. Thank you.